Hi, in this video I'm going to go through a code of chapter 8 of Grokking Deep Reinforcement Learning. Finally, in this chapter we're going to use deep learning for reinforcement learning. In the previous chapter we saw how the Q-value function was learned using a table, but that table is going to be replaced with a deep neural network in this chapter. The approach is the simplest one for Q-value based learning. In the next couple of chapters, chapter 9 and chapter 10, more advanced Q-value learning techniques are introduced with deep learning. And finally, in the last two chapters, 11 and 12, actor-critic agents are introduced like TD3 and PPO. But let's start with the basic one here, which is chapter 8. We're going to use an NFQ agent. So let's go to the code again. In this case, instead of running it through the Jupyter notebook in Google Collaborative as I've been doing in the past, I just copied the code locally and I'm running it in VS Code. So just to go over the code in the, let me go to the here. So there's going to be some helper functions to create the environment, to display the environment that we're going to use is we're going to train a carpool environment. This is very common in reinforcement learning. We want to balance it, and notice that this is more a more advanced environment than the ones that we saw in the previous chapter. This is a contiguous environment, at least in the observations, in which you have a position, which is a contiguous quantity. Also, we have the derivative that is the speed, the horizontal speed. We also have the angle of the bar and the angular velocity. So there's a total of 4 contiguous quantities, infinite quantities for observation. For the action, this could be more complicated, and you can apply a force to the left and a force to the right to make it contiguous. But to keep it simple and be able to use just a Q value agent, we're gonna keep the actions to 2. Either put a constant force to the left or constant force to the right. So of course it will be better if we make it continuous, but that will require probably an actor-critic agent, most likely. Okay, so that is the environment that we're going to train. You have 4 input variables and 2 output variables indicating if you want to go left and right. So we have some methods to create the environment, to display it. We're not going to go through that. The most important is the FCQ class, which is basically the one that implements the deep neural network. There's the strategies, the greedy strategy. The greedy strategy is used for evaluation only. It's basically given the Q function, you're gonna just take the argmax of the Q values. So that's why we can only have in this case we only need the Q value because we're doing the argmax. That's your policy. And for training, we want to do exploration, especially at the beginning, and we are using epsilon like we've done in previous videos. At the beginning, the epsilon becomes high, and there's higher probability of taking a random action, and otherwise you take the argmax. That is the action that maximizes the Q value function, and the Q value function is the expected long-term reward for that particular action in a particular state. The NFQ is the class that implements the agent. So we're gonna debug through all of this. So let's go into it now. Okay, so I'm gonna put a breakpoint in here. I set up my launch just to run the script, the current file. Very simple. Okay, so let's go here, and I put the NFQ in a separate class, and the strategies and the FCQ. This is the one that implements the neural network. Okay, so let's just run it, hit F5. Okay, so the author is gonna, to get better statistics, is gonna run it over a set of seeds, and so it's gonna run it 5 times for different seeds. And here's the configuration for the environment. We use the carpool, which is the environment that I just described. A gamma, this is for training, and the learning rate should be around, it's not here, but the goal of the reward goal is going to be 475. So what happens here in this environment is that you're going to get a 1 point reward every time that you stay alive. Every time that in the environment it terminates, it has a failure when the pole it has an angle higher than a given threshold, or the card goes outside of the horizontal threshold. So if you go outside of the horizontal or angular threshold, you're gonna go to a termination state. And while you stay alive, you're gonna get a 1 point reward, so it's gonna accumulate pretty quickly. So you expect to go to 475. Yeah, so this is the length in minutes for training, the maximum episodes, and that's it. That's about it. We're gonna have the first. We're gonna have a lambda for our neural network in here. So let's put a few breakpoints. I'm gonna pause the video to add those breakpoints. Yeah, I'm adding breakpoints in here. Probably I mentioned it in previous videos, but I'm gonna mention it just in case. I believe that one of the best way to understand a code base is just debug through it, because when you read the code, sometimes you don't know how the values look, how the types look, especially in Python that is not strongly typed. Sometimes you at runtime is where you know the types that you have, and the types tell you a lot of about what is happening. You understand better the algorithm like that, and yeah, it definitely helps in the understanding. Yeah, so I put up breakpoints in the deep neural network here. The number of states is going to be a parameter, and the number of actions. We know that this is going to be 4 and this is going to be 2 for the carpal example, but it's parameterized in case you want to use it with another environment. And we're going to have the optimizer is going to be a root mean square prop. And notice that one of the inputs is the network, and from the network we get the parameters and the learning rate. The learning rate is the other parameter. It's going to be just below. You can see here 0.0005. So this is important because these are the weights of the network, and that's the way that the optimizer is going to know about what are the weights of the network that it has to change. So first you complete the gradients using a loss function. In this case, for the Q value, you have an estimated Q value and an actual Q value, get the difference, get the loss. With that, compute the gradient using backbar propagation, and once the gradients are computed, this optimizer is going to use those gradients to update the weights that are listed in here. So that's how it's going to train that neural network in this reinforcement learning training environment. Okay, so as mentioned before, we're going to have a couple of training strategies. They are captured as lambdas as well. The first one is for epsilon greedy for exploration, and the other one is just pure greedy for evaluation. Okay, the batch size is going to be pretty big, 1000. Number of epochs, the number of times we're going to run this training, 40. So yeah, we'll get the environment settings. Those settings here we capture in independent variables. Now we're going to create the NFQ agent. This is going to take us, we pass the training strategy, evaluation strategy. This is going to be provide our training as well, I think. Yeah, it's going to provide all the training inside of it. So we have the deep neural network model. We have the optimizer and the learning rate, which is just a scalar, and the scalars of the batch size and the epochs. So let's put a breakpoint here, and let's go inside of it. Actually, their training is not inside of here. This is just the constructor, but the agent has a train method, which is called here. This is where the training loop appears. So here we create environment, and we create a new environment for each seed. We're gonna run it for the number of seeds, and then we get the results from the training and just append it so that they can be plotted. Okay. So let's go to a constructor. It does take us to a constructor. It's basically capturing the local variables. That's about it. Okay, so now we're gonna create the environment. This is just gonna create the OpenGym make. Yeah, I just passed it too fast. It's gonna be this, create the environment. I had to make some modifications to this code because it was not able to run because of versions. PyTorch modifies certain things in the API. That's why people like to use Docker and virtual environments to avoid problems with the versions. But anyway, so I'm gonna go inside the training loop, which is the core of the algorithm, the most important part. So yeah, we're gonna do some initialization task, take the start time of the training, create a temporary folder, capturing all the parameters. We're gonna make the environment. Okay, so we're gonna call the function again. We go to OpenGym. Now we create the environment, and we put some wrappers around it. And these are conveniences like using the decorator pattern in design patterns. This is for plotting the carpole, balancing the carpole. Yeah, for displaying that. Okay, so we're gonna set the seeds in the different places in np random, numpy random, and also in pytorch. Okay, now we have the environment, and we're gonna take the out of the environment. We take the observation space and the action space, the number of actions and the number of observations, and we know that it's gonna be 4 and 2. The 4 variables that I described from the carpole: position velocity, angular velocity, and angle. And the actions is either go left, force, constant force to the left, or constant force to the right. Okay, so now this is our Q function. So we're gonna instantiate it. So this is gonna instantiate our deep neural network. We know with the given parameters. So let's create it. Let's go inside of it. And this takes us to the lambda. And the lambda is gonna take us to the FCQ, which is a class that creates the neural network. Now we have the activation function, which should be a ReLU. Yeah, it's a ReLU. And this neural network is very simple. It's just a multi-layer perceptron. It consists solely on fully connected layers and the ReLU activation layers. This just for this, as mentioned before, this is a very basic example. For the next chapters, introduce better examples. Although this book really focuses on more on the reinforcement learning techniques. It doesn't focus as much in the architectures of the neural networks underlying. Like the MATLAB documentation for the reinforcement learning, usually they use multi-layer perceptrons for this. Although you could also use things like transformers and things like that. Okay, anyway. So these parameters tells you the number of layers that you're gonna have. So let's just print it out to see what we got. So we got 512 and 128. So we're going to go from 4 to 512, and from 512 to 128, and finally to 2. So our first one goes from 4 to 512. Then we're going to create a module list. Notice that we start with an input layer and then followed by the hidden layers. So we're going to have a total of only one layer. So it's going to be a hidden layer that goes from 512 to the second one. You see the index here. So it goes from 0 to 1. So it's going to be from 512 to 120, and you can see it in here. You see 512 to 180. Whoops. Let's print it out again. There you go. Okay. So then finally you go from 128 to 2 in the output layer. Just print it out. And we have our linear layers. You can see it in there. Yep, 128 to 2. Okay, so the device is going to be CPU, but we have a GPU available, so everything's going to be loaded in the GPU. So it's going to be the only GPU that I have, CUDA 0. And then the device, we're going to set it in PyTorch and just move everything of this neural network into the GPU device so it can be optimized. Okay. So now we have our deep neural network, our multi-layer perceptron, and then we're going to get our optimizer, and it's going to take us to the lambda. Just create the RMS prop that we just saw. Okay, now we have our optimizer. So we have our training strategy, the epsilon greedy and the purely greedy for evaluation. We already mentioned that, and now finally we're going to enter into a training loop. Okay, so take the start time, reset the environment, and when I reset the environment, I get the first state. And then start the reward data collection, and then we're gonna basically go infinitely until we reach a termination state. And then we collect the data and break. And once we break, notice all of these commands. I'm not gonna go into details through them, but it's going to take the mean, standard deviation, average, some statistics. I'm going to put some debugging message, basically to be able to print the training progress. I'm not going to go through that because that's not the heart of the algorithm. Okay, so let's go inside. One of the incompatibilities that I found is that the state came in a tuple. So I had to take the first element of the tuple, which is the actual state. And you can see then here, the state is basically just the four scalar values: position, uh, horizontal velocity, angle, and angular velocity. That's our state. Okay, so now with the existing state and the environment, we're going to take an interaction step, and that is where the agent is going to take the decision whether to push the cart to the left or push the cart to the right. That's where it happens. So the strategy that the author has in here that is going to improve over the book is that it's going to collect a batch of data, and then once the batch of data is collected, if you have enough experiences points, which is basically the state, reward, next state, and termination value. Once you have your experiences, it's gonna use that batch to do the training. You see here the online model and optimized model. This is where the training happens. But this is data collection. So we're gonna spend a while collecting data. Of course, I'm gonna post a video when this happens. So when to collect the data, it's basically taking the training strategy, which is gonna be an epsilon greedy, using the model. So you're gonna pass the online model, and Python, I understand that it's gonna pass this as a reference, not by copy, and then you pass the current state. So let's go to the epsilon greedy. So the epsilon greedy, since we're gonna take a value out of the model, since we're going to take an action, we don't want this to be part of the Q training, the Q value training. So we put torch no grad. We don't want to compute gradients when we pick the action, because we're using the same model to pick up the action. So for the given state, the model is going to give us the Q values, the long-term rewards expected for the two actions that we have, going left or going right. So we're gonna detach. We're gonna send it to the CPU. We're gonna detach it, send it to NumPy, and squeeze it, and we have the Q values in here. So notice that now we're going to the model, and the model is gonna do the forward. Forward is basically given the state, the model is gonna pass it through the neural network. So the first part we have to format it, and basically it's converting the PyTorch NumPy array into a PyTorch tensor, because the neural network works with tensors. So we send it to the device because we're in the GPU, so we have to create the tensor in the GPU and unsqueeze it to have the batch dimension. Okay, so now that we have our tensor, and you can see it in here, you're gonna see the shape. You can see that it's just an experience point, it's the observation, and let's see the shape. Is 1/4. That's why we use on squeeze on 0 in here. Okay, now we're gonna pass it through the activation function, which is a relu. You can see it in here. It's a relu, and then the input layer. So we pass the tensor to the input layer, and it's gonna give us a tensor of size 512, because those are the hidden layer sizes. You can see it's 512 now, and the next. We pass it to the hidden layer and another activation layer. We only have one hidden layer. So now the X is gonna be size 128. You can see 128. And finally we pass it through the output layer, which doesn't have an activation function, and pass the 128 size vector, and we're gonna have a size of X. So what that gives us is the Q value for the given state that we are at. The input was a state, and the output is the Q values for the actions. So you can see that the Q value, expected long-term reward for going left, is higher than the expected value of going right. So you can expect that if we take an argmax, we're going to go to the left, but in training is important exploration. That's why we have the epsilon that might take any of the two randomly. So we're going to see now the Q values. You can see it here. It's the same. Now since we go from tensor to NumPy, we go back to NumPy, so we have a NumPy array. We're out of the GPU, and randomly the epsilon value should be how much? 0.5. 50% probability of going random or going greedy. So we went random. and the action is going left. It happens to be that the going left is also the greedy action. So when we keep track, if we taken an exploratory step or a greedy state, it's gonna tell us that we took the greedy step, although we really took. You're gonna see it in here. Whoops. So this is gonna say that, yeah, false. So it said that we didn't took the exploratory action, but we really did. Just happened to be the greedy action. Okay. Anyway, so that gives us our action, and from the action we just pass it directly to environment, and the environment is gonna give us the new state, that is the transform a card an angle using the dynamics that the environment is modeling, the physical dynamics. And then we have the reward of 1 because we are still alive. This is not a terminal state. And now we have our experience point. This is the tuple experience. And this experience tuple, the state, action, reward, and next state, and the termination flag, is going to be appended into a list of experiences. And then we're going to sum the reward at the end, because this is for data collection, and the time step, etc. So now we're collecting in this. We're going to keep collecting. You're going to see that we're going to keep collecting. That experience array now has a size of 3. Now has a size, you're going to see the size of it down here. So it has a size of 4, and keep running. It's going to keep growing. Whoops. Okay, it's gonna keep growing. So we want to get inside of here. It has to reach to 1000. So we're gonna put a breakpoint here and hit F5. Okay. Whoops, so it didn't get there. So it went to evaluation. What in evaluation, as mentioned before, it's gonna use the evaluation strategy, which is a purely greedy, and it's gonna take the greedy action and evaluate the model. But the model hasn't been trained, so you don't expect anything. I'm not gonna go much in detail in here. So let's get out of here. So it didn't get into here, so let's keep running. Okay, this is for saving checkpoint. Finally it got into here, we have more experiences. Let's see how many. We have the same amount of experiences as the batch size, so we have the batch. And now we're gonna convert the experiences. What this is gonna do, I'm not gonna go into much details of this, but we have an array of experiences, and that's not what we want to optimize the model. Remember, we want tensors. So we're gonna convert it, the experience as an array. We're gonna convert the list into an array. So now we're gonna see the shape. It's gonna be 1024 by 5, but we're gonna transpose it. And by transposing it, we get a 5. Why we have 5? We have 5 because we have the states. So we want to have a tensor, a tensor of 1 dimension for all the states. We want another tensors of 1024 values, a batch tensor for the rewards, and another one for the next states, and another one for the termination condition. So we're gonna transform it like that, and you can see that it's gonna pick up all the dimensions and it's gonna stack it vertically. So we're gonna see here what happens. So it's gonna iterate through that. So I'm gonna just hit F5 here, and now it's gonna use the online model. But let's see how the batches look. So whoops. So now notice that these square brackets in here. So we're gonna create a list of 5 tensors. So you're gonna see that this is a list. It's a list, and the length of the list is 5. So we have 5 tensors. Let's pick up the first one and take the shape of that tensor. Okay, so that didn't work. Let me see why. Yeah, this is not MATLAB. I have to use square brackets to pick up. So for the first one, you can see that it has a shape of 4, and this is because the observations have 4 values of position, velocity, angle, and angular velocity. So we have 1 batch only of states. The next one is going to be 124 by 1 because it's the rewards, And the rewards is a scalar. You can see it in here. It's a scalar, so it's just only one. And the third one is the next state. So it's gonna be 1024 by 4, because this is whoops, is the third one. Yeah, exactly. This is the next state. So what is the third one? When we take the experience here, it's a terminal state. So the third one is it tells you if it basically failed, if you have to stop the simulation. Okay, so now that we have the tensors, and you can check, we can check here, type batches 0. So we have a ND array. It's a NumPy. We still are in NumPy. So we're gonna load it. So you can see that those NumPy arrays are gonna be converted into tensors in the load method. You can see it here. So all those 5 NumPy arrays are gonna become torched from NumPy into a float tensor. And not only that, not going to convert it to tensors, but load it into a GPU. So that's all what we're doing there. So now we're ready to apply those input tensors of the experiences into the agent. So we're going to optimize the model with all of them. Okay? So we're going to run it in the range of the epochs. So we're going to run all those batch experience by 40 times. So let's do it only one step. Okay. So first we get the experiences. We have the different tensors. Each one has the size of the batch size, and we have it here, although we don't use it. And then when we train the Q value, now I've been talking like for 26 minutes, but this is the most important part here. Pay special attention. This is basically where the training is, because what you want in your Q value training is to predict the long-term reward of the suit, so that basically your agent can go into a direction that maximizes the long-term reward once it is trained. So how do you predict what is expected? What is the predicted long-term reward? The predicted long-term reward is the Q value from the model. You get it here. You see self online model, you pass it the state and you get the long-term reward. You gather it and you get the value. So you get it out of the GPU, I suppose. Or okay. What the gather is doing here is basically applying the actions. It's basically when you get the state for the given states in the model is going to give you the Q value function for that particular state, and it's going to give you 2 values. The Q value for the left action, applying the left force, and the Q value for applying the right force. So you're interested in taking the actions, getting the Q value for the corresponding action. So remember that we have a batch of actions in here that was collected from the experience samples. You can see that sometimes you go left, sometimes you go right. So the gather is going to go into the second dimension, and it's going to apply those values to get the Q values for those particular actions. So you're basically getting the predicted value for that particular experience. So that was easy. It's basically, use the actions from the experiences and the predicted value from the model. That is the predicted Q value. But you want to have a difference between that and the actual Q value, the actual long-term reward. And yeah, it's similar to what the other videos we have seen in the other videos. You take the reward, the current short-term reward, and you add it to the expected long-term reward. So the expected long-term reward is going to be, again, we are using the online model, but with the next states. So the next states are going to give you the reward after this particular experience point. So for this experience point, we have the reward, and then we apply the gamma for this is for when the reward loses power over time. It loses, the value decreases over time. In this case, I think it's 1. So it doesn't have any effect. Yeah, it is 1. So the max is going to be basically, given the next state, we're going to take the argmax. Notice here that we take the maximum. We detach it. We don't want gradient computation in here. And then we squeeze it to match in size, in shape. So basically that's your long-term reward. So it's basically the current reward. This is a real value, and the predicted one. So this is estimated. The rest is estimated. This is the Bellman operator. We have seen it in other videos. So we take the difference, and from that we basically get the square, multiply it divided by 2 and get the mean, the average, the square average, and then we clear the gradients. We have to clear the gradients from previous iteration in the optimizer. Then we take that value loss, and this computation is going to have a computational graph that is computed with all the weights of the network and with these operations that we are doing here. And then from that, it automatically, symbolically, is going to compute the gradients of each of the weights relative to the weights. And from that, we use the optimizer, which know what are the weights of the network. Apply a step, and then you have the train network. Okay, so that's basically a training step. So that's how you learn the queue. So you keep doing that many times. I'm gonna put the break, take out of the breakpoint. So keep doing that for the number of equals. It's like 40. And then we're gonna step out of here. So yeah, that's gonna take us, let it keep running. Yeah, we're gonna have some checkpoints, and this is to store our weights, some important information that we want to keep track of. Let's get out of here. And yeah, finally we're gonna run it for multiple seats, and let's go all the way to the end. Okay, again, the training loop is gonna keep going, gonna pause. You can see here the progress of the training, and for each seed it's gonna write to the goal of more than 400 reward. In the first run that I did, it didn't reach the goal because I wanted to basically get debugging through the parts as soon as quicker. But now I increased the maximum number of episodes. It was reaching a maximum number of episodes at 100, so I changed it to 10,000. And now it's improving in the average reward. You can see that it's 100 right now. It was 1731, and the evaluation is also close to that as well. So of course you have to run it a lot, but for debugging it's better, even if it doesn't mean it's code, it allows you to go quickly through the code. Okay, I went to do some shorts, and after that it improved in evaluation to a reward of 200, halfway through the goal of 400. Sometimes it arrives, for some reason it got stuck in here, but basically the idea is that it's going to train the queue function to take the left and or right more optimal action. And initially with few episodes it's going to look like this, eventually it's going to be more balanced, and it gets more stable over time. But again, this is not the optimal queue value function, the NFQ. More advanced, like the DDPG agent, is going to be introduced in further chapters. That's it for the video. Have a good day.